Far across the universe, astronomers began finding something that should not have been there. Yet, in regions so distant they belong to the universe's earliest visible history, astronomers found something already fully formed. Enormous black holes sitting inside galaxies that still look young and unfinished. These were not small objects beginning their existence. They already contained millions to billions of times the mass of the Sun. The observation creates an immediate visual contradiction. The universe itself still appears young, yet some of its largest known black holes already look fully established. That changes more than a number on a chart. The accepted timeline depends on having enough time for everything to form step by step. But each new discovery pulls that starting point closer to the beginning, leaving less room for the process to fit inside what is actually observed. The problem is no longer the existence of supermassive black holes. The problem is their timing. Objects that seem to require enormous stretches of cosmic history are appearing in a universe that does not appear old enough to have provided it. Somehow, the outcome is already visible. What happened during the universe's earliest era to make that possible? The easiest escape route was still available. Maybe the first discoveries were unusual. Maybe a rare object had been mistaken for a broader pattern. Maybe later observations would shrink the problem instead of expanding it. That is not what happened. More surveys looked deeper into the distant universe. More telescopes examined different regions of the sky. Instead of the early giants disappearing, additional massive black holes kept appearing. Each new detection didn't stand alone anymore. It added to a growing list that different telescopes kept confirming. What started as isolated findings began lining up into the same pattern again and again. What first looked like a possible exception began behaving like a recurring feature. The safest explanation started losing ground. A measurement mistake can explain one observation. It becomes much harder to use when separate observations continue pointing in the same direction. Every new early black hole removed another piece of that escape route. The possibility that the entire problem came from a single error became harder to defend. The conflict was no longer attached to one object. It was attached to a growing collection of them. The timeline pressure remained, but now it appeared in multiple places at once. The uncomfortable conclusion was becoming difficult to avoid. Different observations were repeatedly arriving at the same destination. If these detections are real, then the problem runs deeper than a mistaken measurement. Either black holes can reach enormous sizes far faster than expected, or something important about their beginnings has not yet been fully accounted for. Researchers did not have to abandon the entire framework to see a possible way forward. Instead, they began looking for paths that could shorten the journey. One possibility was simple in principle. Maybe some black holes did not begin as small objects. If the earliest seeds started out unusually massive, then part of the growth process would already be complete from the very beginning. Another possibility focused on behavior rather than starting size. Perhaps during certain periods, these black holes consumed surrounding material far more efficiently than expected. In practical terms, that would allow them to gain mass much faster while still remaining inside known physics. For the first time, the pressure seemed to ease. The timeline had not disappeared, but it no longer looked impossible. The giant black holes appearing in the young universe could be imagined as the result of a head start, a faster growth phase, or some combination of both. The contradiction that had seemed so severe began to look more manageable. The observations remained challenging, but they no longer appeared completely trapped outside the existing framework. There was now a visible path connecting the early detections to known processes. And if that path was correct, future observations should slowly reduce the tension rather than make it worse. The new explanations held together for a while. If some black holes started larger, the timeline gained breathing room. If they experienced periods of unusually efficient growth, the gap narrowed further. The conflict did not disappear, but it seemed possible to contain. Then the observations pushed deeper. Astronomers continued looking farther into the early universe, and massive black holes kept appearing in regions representing even earlier moments of cosmic history. The pattern was no longer standing still. Each new detection effectively moved the problem closer to the beginning. That created a visible form of pressure. Every attempt to solve the timeline challenge depended on having enough history available for growth to occur. But as the observations reached earlier and earlier eras, the available history kept shrinking. The starting line moved backward. The clock became shorter. The proposed explanations still survived in principle. Larger seeds could help. Faster growth could help. But each newly discovered early giant demanded that those solutions operate within an increasingly limited window of time. The situation had changed. The issue was no longer one remarkable black hole sitting at the edge of expectation. The issue was that the universe kept revealing additional examples in places where the growth window became progressively harder to explain. The observations were not removing the tension. They were extending it. And that raises a more difficult question. If future observations continue pushing these massive black holes deeper into cosmic history, how complete is the current picture of the universe's earliest stages of black hole formation? The black holes themselves are only part of the story. What gives these discoveries their weight is where they appear. They are showing up in the earliest chapters of cosmic history, in periods that astronomers use to reconstruct how larger structures emerged over time. Each newly discovered giant becomes more than an object. It becomes a test of the timeline surrounding it. That creates a broader consequence. A timeline that once seemed dependable now carries more uncertainty. If enormous black holes were already present so early, then every attempt to describe how galaxies formed and evolved must account for that reality. The pressure spreads outward from a single class of objects and begins touching the wider history of the universe itself. The challenge is not just their size. It is where they appear in the timeline. Each one arrives in a window of history that is getting smaller the farther back astronomers look. The challenge is that they reached those sizes in places where the available history appears increasingly limited. That forces a closer examination of the assumptions used to interpret the universe's earliest eras. The observations do not show that existing ideas have failed. They show that some of the most important cosmic clocks may not be telling the complete story on their own. The result is a more cautious picture of the beginning, not because the universe stops making sense, but because the same cosmic clocks used to reconstruct its earliest history may not be showing the full story of what actually happened in those first moments.